So in the last video, I introduced the notion of an approximation algorithm, and we talked about that one algorithm for the minimum spanning tree to approximate the TSP solution. In this video, I want to talk a little bit more about more recent developments and how this works. I put a star next to recent because not all of them are the most recent, particularly starting with our first one, which is this thing called Christophany's algorithm, came around in 1976. So it's actually in theory very similar to this MST approximation that we talked about before. The big difference is it does a much better job at taking the MST and turning it into this kind of cycle around the graph. But in theory, it's a very similar algorithm. It has a lot of complications in it about kind of like dealing with even and odd vertices depending on their out degrees. But I'm not going to talk about the details of that algorithm. It's just taking an MST and doing a smarter job at turning it into a final solution. Now, Christophany's algorithm turns out to be a 1.5 approximation to TSP, which is better than our 2 approximation from before. So using our 100-mile optimal solution example, Christophany's algorithm would find a cost at most 150 miles. So it's only 50% worse than the optimal, which is pretty good. And so then kind of a natural question after Christophany did this work was, can we do better than a 1.5 approximation? And the answer was, we don't know. People thought about this for 40 years or over 40 years, and no one was able to come up with a better approximation. But this year, there were some recent headlines about some Allen School professors and a grad student that actually did break this record. So this is an article from Quanta magazine, and the headline says, "Computer scientists break traveling salesperson record. After 44 years, there is finally a better way to find approximate solutions to the notoriously difficult traveling salesperson problem." Now, in the old kind of Christophany's algorithm, we talked about that 1.5 approximation. And so the question is, how much did they beat this 1.5 approximation by? Well, their algorithm has an approximation ratio of 1.49999999999, lots of nines. I think there's 36 nines in total. They beat Christophany's algorithm by the most minuscule amount possible. It is a tiny, tiny improvement over kind of what we had before. So your first question might be, why the hell did this make headlines? Like, this is such a minuscule improvement on something. Why does anyone care? And there are actually lots of reasons people care about this. This traveling salesperson problem is one of the most well-studied problems in CS history. And after Christophany came up with his 1.5 approximation, no one for over 40 years was able to improve that algorithm by even a little bit. Now, when everyone's trying to work on one problem and no one's making progress for 40 years, you start thinking that it's a lost cause. And so people are losing hope that there was a better solution out there. And so finding this improvement, even though it's so absurdly small improvement, is a proof of concept that something better exists. And now there's hope that we might find an approximation algorithm that's much better. And that has huge impacts, right? You know, I don't have any particular love for big companies like Amazon, but they need the algorithms like this to help them figure out how to route shipping deliveries around a city or around the country. And even these minuscule improvements can vastly improve the outcome there. Maybe not this such minuscule improvement, but if we are now able to find a 1.4 approximation or something like that, then we've really opened up the doors here. Now, one of the things that's also really interesting here is the fact that in order to do this, they had to use a lot of new mathematical machinery to prove their result. So they use this thing called the Geometry of Polynomials to go about and help prove that their algorithm was actually better. Now, the hope here is that since they're able to solve this kind of unsolved problem for a long time using this new tool, maybe this new tool has merit. Maybe we should start thinking about how to apply it in other places where we've had trouble finding a solution, and maybe it'll help us. So it's kind of helping bring a new perspective on how to solve problems, and that could hopefully be used to solve other things. And kind of finally, computer scientists are really interested in kind of what's the nature of computation. like what things are and aren't possible to compute. And so this actually does kind of give another avenue to explore kind of what might be the fundamental limits of computation, even if it's just in this traveling salesperson context, but more broadly too, questions of what we can and what we can't compute efficiently. So that's why this matters. This is why it made headlines, is it opens up a lot of doors, even though the contribution itself, the actual improvement, is so minuscule. It opens up hope, and it provides new tools to try to hopefully analyze other problems. And that's why it makes headlines. Now, I want to give you a brief kind of idea of what they did and how it works, but I can't give it all the detail that justifies it. I'll link to that Quanta article that actually does a really good job with examples explaining kind of in detail what they're doing, and some more history of this problem. So their algorithm is actually very similar to Christophanides' algorithm in spirit. Just like how Christophanides' algorithm was our MST approximation, but changing how we go from the MST to the final solution, they made another change. Instead of using a minimum spanning tree, they generate a tree using what we call a randomized algorithm, an algorithm that uses random numbers to help it make choices along the way. So it generates a random tree and then uses a process similar to Christophanides' algorithm to take that tree and turn it into a cycle. Now, it turns out that idea is actually relatively straightforward, given, like, I'm glossing over a lot of details here, so obviously it does not make a ton of sense. But like, the algorithm itself isn't crazy complicated. But what was really hard was to prove that algorithm was somehow better than Christophanides, that it resulted in solutions that were better. And so that's kind of a key insight in a lot of work that happens in particularly theoretical computer science, is coming up with algorithms is only part of the battle. Like, you have to come up with your algorithm and then prove that it's in fact better, or that prove that it's correct. And so a common challenge that work in computer science faces is coming up with this kind of proving that what you're doing is actually the right thing and actually does yield better results. And so that's kind of gives us like kind of a high level description of kind of how we've given up finding exact solutions efficiently in favor of these approximations. We'll talk more on Monday about why we've kind of given up on these exact solutions. Kind of, there's this fundamental problem that we still don't know the answer to that makes it seem that finding an efficient algorithm to TSP that solves it exactly is not going to be possible. So we're going to talk about this P versus NP problem on Monday, talk a little bit more about these kind of limitations of computing. But hopefully you can see something interesting here, in that a trend in modern computer science is kind of trying to solve problems approximately, because we have a lot of really interesting problems that we don't quite know efficient solutions to solve exactly. And this tells a really interesting history of these approximation algorithms in this particular traveling salesperson problem context. But hopefully you can see that there's lots of exciting work to happen. And you could see that, I did skim over lots and lots of details, so it's totally okay if all of this doesn't make complete sense. But I think you're able to follow along, right? I'm talking about minimum spanning trees. I'm talking about DFS. All of those things are building blocks people use today in order to solve kind of the problems at the forefront of computer science. Now, sometimes they have a lot of extra details that don't make any sense to even me, but we have a really nice solid foundation to have conversations about this stuff. Now, if you're coming to class today, we don't have any formal practice problems to talk about these things. It's going to be more about more of an opportunity to do question and answers. So the TAs and I will be there to answer any questions about this stuff, but we don't have any formal practice. So if you have any questions that come up, please come to class today and we can talk about them. But otherwise, I hope you all have a great weekend. I hope you found that this was at least a little bit interesting.